All right, let's look at this example problem. We have an archer that's shooting an arrow 75 meters to a distant target. The bullseye and the release point on the arrow are the same, so they're on the same height. We're going to call that height y equals 0. At what angle must the arrow be released to hit the bullseye if its initial speed is 35 meters per second? All right, so let's work through this. Let's start by looking at the equations that we have to work with. We have y equals 1/2, right? at squared plus v naught y. Now let me put this a sub y plus v naught y t plus y naught, right? And we have x equals 1/2 a xt squared plus v naught xt plus x naught. Right? So we've already mentioned we know a few things about this. First, what's the final y position? It's 0, right? What's the y acceleration? Well, that's going to be the minus 9.8 meters per second squared because of gravity. What is the final y position? Or the initial y position? 0, right? So the only thing we don't know in the first equation, we don't know time, right? We don't know t, and we don't know, we don't completely know v naught y, right? We do know some things about v naught y, and we'll get to those in a minute. As far as x's goes, well, we know the final x, that's 75.0 meters, right? We know that the acceleration in x is 0 because there's nothing affecting in that direction. We know the initial x position, that's 0. All right, again, in this equation we don't know t, and we don't really know v naught x. All right, but there's a relationship between v naught x and v naught y. All right, so we know that v naught x is 35 meters per second times the cosine of whatever angle we fired at. And we know that v naught y is 35 meters per second times the sine of whatever angle we fired at. All right? So we know we got the cosine, we know we got the sine. This gives us a relationship, if you will, between these two. Let's go ahead and let's simplify the equation for y as much as we can, and then let's simplify the equation for x, and let's see where that puts us. So starting with y, all right, 0 equals minus 1/2 9.8 meters per second squared t squared plus 35 meters per second times sine of theta plus 0, right? Nope, times time, pardon me, times time plus 0. All right, so that's our equation in y now. We stuck in this bit for v naught y. We stuck in the fact the acceleration is minus 9.8. We stuck in the fact that it ends at 0, it starts at 0. Put all of those in. Now there's one thing we can do right away with this. We can go ahead and we can divide by t, because we have 0 here, 0 there. We have t squared and we have t. So if we divide by t, the fact that the t is there to be divided out simply tells us that one of the times when that if you don't fire this at all, or if you fire this straight up, basically is what it's saying, you're going to be at the same point, right? But so we get rid of one of the t's. That gives us 0 equals, I'm going to multiply through the 1/2, equals 4.9 meters per second. Meters per second squared times time plus 35 meters per second times sine of theta. All right, and we can solve for t. I'm going to say solve for t is 35 meters per second. 35 meters per second divided by 4.9 meters per second squared times sine of theta. That's t. Okay, so we've got an expression for t. Now let's take a look at x. All right. All right. Let's stick everything we know about x into the x equation. So it gets simple pretty quick. 75 meters equals, there's no term due to acceleration, so that's 0 because the acceleration is 0, plus v naught. All right, and v naught x is right up here. V naught x is 35 cosine of theta. Right, v naught x times time, plus the x naught, where we start, is 0, so plus 0. All right, very simple equation. 75 meters equals 35 meters per second times cosine theta times time. Let's solve for time again, and we get time is 75. Time is 75 meters divided by 35.0 meters per second times cosine of theta. Oop. All right, so that's what we get for time. This is the time based on the y bit. We still don't know theta, the angle we fire the arrow at. This is the time based on the x bit, and here we also come down to an unknown theta. And what we're after in the problem is at what angle, right? So what we're going to do, is put them together, right? And so we're going to say this equals this. These are both the time that the problem takes place over, right? Those are both times. Solve for theta in a sense, so I'm going to take this, I'm going to say sine theta times cosine theta is, it's going to be 75 meters times 4.9 meters per second squared divided by 35 meters per second times 35 meters per second. Right? And you'll notice in the top we have meters squared per second squared. In the bottom we have meters squared per second squared. All the units cancel out as they have to, since we are looking at sines and cosines here. And so I'm going to go ahead and go over here and multiply this out real quick. 75 times 4.9 divided by 35 divided by 35, and we get, that probably needs a few more, pardon me. Oh. 75 times 4.9 divided by 35 divided by 35. Okay, so we get 0.3, right? So 0.300 or 0.30 is what we get for this. Okay, so now we're going to go at getting an answer to this in two different ways. First, we're going to use the trig identity. Now, do I remember the trig identity for sine times cosine off the top of my head? No, I don't. So often when I need a trig identity, I just go to Google. I know sine, cosine, sine, cosine, trig identities. Okay, sine, cosine, trig identities, trigonometric identities from Purple Math. Trigonometric identities from Purple Math. We're looking for sine times cosine, and here it is right here, right? That's the equation we're after, double angle identity. So let's go into here. We're going to put sine of 2 theta equals 2 sine of theta cosine of theta That's a trig identity that we found. So this bit right here, solving for that, sine theta cosine theta is 1/2 times the sine of 2 theta. All right. So that means 1/2 sine of 2 theta equals 0.30. 1/2 the sine of 2 theta equals 0.30. So sine of 2 theta equals 0.60. We take the inverse sine. All right. Let me go get what that equals real quick using Excel. Okay, so the inverse sine of 0.60, and in Excel it's always going to be in radians, so I have to convert that to degrees. So I get 36.9 degrees, right? Okay, 36.9 degrees, and that means that theta is going to be half of that, 18.4 degrees. All right, 18.4 degrees. Now, that's not the whole story. And I'll tell you why that's not the whole story. This isn't the only solution. All right, so let's think about it for a second. We're talking about the sine of 36.9 degrees, right? Let me draw an axis here. I'm going to draw 36.9 degrees. The sine is this vertical height, right? We're talking about we have our circle, right? And our axes, and the sine is the vertical height. Well, there are 2 points here with the same vertical height, right? And this angle and this angle are the same for those 2 points. The reason this is an issue for us is, like, normally over here, this is not part of inverse, this would not be an angle in the range we're after, but we've got the 2 theta in there. Right? So what is this angle way over here? This angle way over here is 180 minus 36. Right? All right, so let's clean this up. So we now know that 2 theta equal to 180 minus 36.9 degrees is also a solution. And so that gives us a solution that's theta equal to, let's see, 180 minus 36.9 divided by 2, 71.5, 71.6 degrees. All right? So what I'm saying right now is we have 2 solutions. One is theta is 18.4. The other is theta is 71.6, right? This also happens to be 90 minus 18.4. So if you look at it, the 2 solutions we have are an angle like that, right? That's 36 degrees there. I'm sorry, 18 degrees there, and an angle that's like that, that's 18 degrees there. So 18.4 degrees here, or 18.4 degrees there, are actually both solutions to our problem. One of them is a solution where it arcs like this and goes over. The other solution where it arcs up and comes back down in the same spot. So there are two solutions. So this question up here at the top is a bit of a trick question. Will the arrow go over or under the branch? The answer is yes, it will. So here we are. We have our first solution, 18.4 degrees. Our second solution, 71.6 degrees. Now, I'm going to show you another way to get at this. Suppose you don't have your trigids, your trig identities, right? Oh, all right. Suppose you don't have those. I've already set it up over here. I set up theta going from 0 all the way down to 90. Actually, let me just show you how to do this. All right? I'm going to show you how to do this. This is in Excel. So here's theta. Sine of theta, right? I have to do sine of radians of that cell, right? Cosine of theta, I have to do cosine of radians of that cell. And then this is just the result of the sine times the result of the cosine. Now, I'm going to grab these like this. I'm going to grab the corner. I'm going to start dragging it down. Now you can see over here on the lower right hand side of where I'm dragging, it's got a number. That's the number of rows I've been dragging for. And I want to go to 90 because I got 1 degree. There we go. I want to go to 90. All right, so Excel fills in for me 1 through 90. It fills in the calculation for the sine. It fills in the calculation for the cosine. I'm looking for sine times cosine equal to 0.3. So I come over here to my table and I start going up and I say, there at 71 degrees is something close to 0.3, right? And if I keep going, I'll find also here at 19 degrees, or between 19 and 18 degrees, another thing close to 0.3. So I can close in on the answer and verify what I'm after using a tool like Excel, and simply by going through and looking at the calculation and saying, oh, and it didn't take me that long to do that. In fact, it took me less time to do this than it did to go through the actual trig. Alright, so now we know the angle. We know the angle question was a bit of a trick question because the angle question actually has two answers. So let's go back up and let's take a look at the second part of the question. There's a large tree halfway between the archer and the target with an overhanging horizontal branch 3.5 meters above the release height of the arrow. Will the arrow go over or under? Right? Will it go over or under? Okay, well, when does it pass that point? Well, let's go back and let's grab one of our equations for time. We have time is 75 meters of 35 meters per second times cosine. Alright, see if I can get that to behave better. Time equals, time equals that. Okay, let's go ahead and let's stick in one of our solutions. Let's stick in 18.4. Okay, so 75 divided by 35 divided by the cosine of radians of 18.4 degrees, and I get 2.26 seconds. Alright, copy all of this, put in 18.4. I get 2.26 seconds. All right, let's do the same thing with the other answer, with the 71.6. And what do we get from Excel? I'm just going to copy that and stick into it 71.6 degrees, and we get 6.79 seconds. So, as you might imagine, the time difference is pretty dramatic between, oh, I'm going to shoot the arrow as straight across as I can versus I'm going to arc it up and have it come back down. All right? happens much faster if we shoot it straight across. Okay, so here's the question. If we are at this angle, let's go back to our equation for y. Where are we in y? All right, let me grab the equation for y. Because we're asking, are we going over or are we going below the branch, right? Okay, now shallow angle. Our equation for y, so we have 9.8 meters per second squared. For the acceleration, that is a negative, right? And when we're doing the equation for y, v naught y is 35 meters per second times the sine of the angle, right? So sine of 18.4 degrees. All right, and so v naught y is equals 35 times the sine of radians of 18.4. V naught y is 11.04 meters per second. All right, so we stick in our 11.04 or 11.0 meters per second times time, and we've got y naught starts out as 0, right? Our time is, in this case, 2.2 seconds, right? 0.26 seconds. So how high? Oh, that's all the way. We were talking about when it gets halfway through, so our time is 1/2 of 2.26 seconds. So our time is 1.13 seconds. Almost made a fatal mistake. 1.13 seconds and 1.13 seconds, right? So that's our height. So minus 0.5 times 9.8 times 1.13 squared plus 11 times 1.13 gives us a height of, so it's going to go over in both cases, a height of 6 meters at the halfway point, right? 6 meters at the halfway point. So it will in fact go over the branch even on the shallow angle. So if it's going to go over the branch at the shallow angle, it's certainly going to go over the branch on the steep angle, and this is 6 meters is its maximum height. Let's just take a look. Steep angle. Steep angle is 71.6, right? So we're doing the same thing. I'm going to copy all of this down. I'm going to change things. So this is now 71.6. Now go over here. That now means 71.6 degrees in, 33.2 meters per second. The time for the shooting it up was 6.79. All right, so 6.79 over 2 is 3.4 seconds. 3.40 seconds. So we stick in our 3.40. We stick in our 33.2. Stick in our 3.40, 3.40 again, right? And what are we going to get for our height? 3.4, 33.2, 4. We'll get a height of 56.2 meters. Okay, so in one instance it goes over the branch because the branch is only 3.5 meters above the height of the arrow with the arrow is launched. And the other case, in the steep angle, it goes up 56.2 meters. It probably goes over the whole tree. All right, I know this is a long problem. It had a lot of different pieces in it. Hopefully this example helps. I'll talk to you later.